So let me just take 1 minute to repeat what I had showed yesterday, and the main estimate is here, right? So what we have done is we've taken a very specific form of kernel, both in position and velocity. Then we calculated the time derivative of the convolution with this kernel, so the quadratic form with the kernel using f. And out of the v grad x, right? So out of the free transport term comes out a regularizing effect. So that we deduce something like this. So I can do. So this is actually a theorem. This is fully rigorous, right? And what does that say, right? Let's spend a little bit of time on various remarks of that. All right, first of all, this is a dispersive effect in Fourier, as a matter of fact. Right, so what is happening is that the Fourier transform of this v grad x operator, right, is another free transport. Where the role of position and velocity is reversed, right? So if you look at that in Fourier in x and v, what happens is when psi is very, very large, it pushes the zeta very far, okay? And, well, the problem is I'm averaging, right? I'm averaging in velocity. So the very, very large zeta, I'm not going to see them, right? There's a filter, if you want to formulate it that way, that removes those very high frequency in velocities. So this is what's going on, all right? You have, for large psi, you have this very, very fast transport along the frequency in velocity. And you're only looking at the frequencies near the origin because of the averaging. And this is it, right? You, therefore, you don't see the others. Now, of course, there is nothing irreversible in this, right? You're just moving things very, very fast. So this is why you only get an averaging with an integral in time here. This is not a pointwise time estimate, and it couldn't be, right? It can very well happen that if you're unlucky at a given time, right? Well, you will have those very large frequency in psi into the region of small frequencies in zeta. What this free transport guarantees is that this cannot happen very often. Now, this is an important point because it leads me to a second remark that I want to make explicitly. We obtain a sort of dissipative estimate that is compatible with reversibility, with time reversibility. So again, what is happening here is that I have d over dt of some quantity of f, right? That is equal to the right-hand side, and okay, the right-hand side doesn't necessarily have a sign, plus something that does have a sign, that is positive. And so this, again, a priori might be a little bit scary because how come I have the same estimate if I reverse time, for example? Well, what happens if I reverse time is that I change all the signs, and then I still get the same estimate. So yes, it is fully compatible. K hat is not positive, right? And in particular, if I change V, and I change the sign of V, and I don't change the sign of X, then K changes sign, and that's the whole point. Now, K is still symmetric, right? If I change the sign of both X and V, then it doesn't change. Right. Now, fair remark, well, this is a very nice simple proof of a classical averaging lemma result. In H1/2. But already at the level of this very, very simple theorem, you have a big gain. And again here, what really this theorem says is that if f is an L infinity LP of x, V, with p larger or equal to 2. Now I'm going to exclude p equal infinity for obvious reason. It doesn't work very well with Calderon-Zygmunt operators. And G is in L1, LQ, right? 1 over P plus 1 over Q less or equal than 1. Then locally in XV, right, what do I have? I have that F is actually in L2 of time, H1/2 of X, H minus 1 of V. That's the result that is obtained out of the estimate. And this is not something that I know how to get easily by any other method. The fact that you still get 1/2 of the derivative in X when G is not in L2, I don't know how to get that otherwise. Now, the reason this works here is that this is really a bilinear estimate. So in some sense, you combine f and g, and whatever integrability you're missing on g can be compensated by a gain of integrability on f. That's what's going on. But out of using a sort of bilinear method like that, again, I don't know how to derive this. So already this very simple result is interesting with respect to the existing theory. And the fourth remark is that this is actually compatible with some hydrodynamic limit. And the key observation here is that the estimate actually works in exactly the same manner if you rescale time. So you have the same estimate with this equation. Now I could take epsilon equal to 0, so the estimate also works, of course, with a stationary transport equation. But it's uniform in epsilon. Now, this is not a super big surprise. Again, averaging lemmas have been used in some context of hydrodynamic limit, and there's 2 papers by Masmoudi and Tayeb, for instance, on that. So it's not entirely surprising that it would work here. It's still a nice perk to get it for free, and to get for free such a uniform estimate. So this is a little bit all that I wanted to say on this basic method. Now I want to give you a little bit of an idea in the next section about how to expand this method to a little bit less trivial equations. The fact that I don't have any derivative, especially any v derivative in g, right? That means that we cannot really use that on Vlasov equations, for example. So it's a little bit painful. And what happens, you know, if you don't have the nice duality in LP space between f and g is another question, because, well, maybe you don't. Maybe you don't have enough integrability on f to compensate for the lack of integrability on g. So the question is really whether we can still do something in a case like that using this type of method. The other thing, of course, is I want to understand also a little bit what's going on with the A of V, right? In particular, if down the line I have to apply that to scalar conservation laws, I want to get the better idea of what's going on there. So I will look at the following system. I'm not going to put derivatives in x. Those are not necessarily very, very hard because the equation itself, as it is written, commutes with derivatives in x. So But I really have in mind here applications more to Vlasov equations or to scalar conservation, which don't require them anyway. I will not consider the case where I have negative derivatives, so when I have a gain of regularity on G. And again, I will take F in LP, right? G in some LQ. L1. And still L1 in time, L infinity in time, which is we could swap, huh? So there's no need for L infinity in time on F and L1 in time on G. It's just, it corresponds very nicely to the type of estimates that you normally have on such kinetic equations. It could even be more complicated if you go and have a look at the papers. We can actually handle different integrabilities in X and V. So F can be in LP1 in X, LP2 in V, G can be in LQ1 in X, LQ2 in V with P1 different from P2, Q1 different from Q2. Again, I'm not going there here. I'm trying to keep things reasonably simple. But here I will not necessarily have the duality assumption on P and Q. Right, so I have two issues when I'm going to try to apply the method before. The F against, so let's write this, the main issue is to bound the right-hand side. And the reason there's an issue here is right, because of the extra derivatives. So if I just try to integrate this by part on K, right, well, the corresponding result will not be a bounded operator in the sense of Kähler and Zygmunt, so I cannot do my duality anymore. And the second problem is that, well, even if I had zero derivative, right, I've lost the duality anyway, because maybe now 1 over P plus 1 over Q is strictly larger than 1, and I'm a little bit stuck. So still we have the following theorem. So I need an assumption on A, of course. And here the assumption is that A is 1-to-1. With the determinant of the reciprocal bounded. Okay. Now this is something that could be extended. To some L gamma, it doesn't necessarily need to be in L infinity, you get the worst result. And and f and g are as above, right? Then again, I have that for any smooth phi, rho phi belongs to some regularized space, so L2 in time as before, HS in X. With S that is given by the following formula. And mu are coefficients that I'm writing here. Now we could again have an even more general formula with gammas, with different p in x and v, but this is a little bit simpler, and it gives you a reasonably broad range of results. Okay. So this still works. You still get something. Okay. As before, because this is still a bilinear method, and I will explain in 5 minutes how we get it. So this is still a bilinear method, and therefore you still get the average in an L2 base of a left space, right? So L2 in time, HS in X. Now, right, the formulas are even simpler. If p is larger than 2, because you see that then nu is equal to 0, right? So nu really measures how far away f is from being in L2. And mu measures how far away we are to being in a dual situation. Right. So if 1 over p plus 1 over q is less or equal than 1, then one also has that mu is equal to 0. Can you see what I'm writing now? Because it doesn't show up on my screen.
The last formula is about mu and nu.
Yeah, all right. So there is a problem. Sorry.
We lost your slides.
Yeah, well, that's on purpose because you were, I mean, you were not seeing what I was writing, so there's not much point.
Okay.
Okay. Yeah, it's super slow. This is usually why I prefer to connect directly with the tablet instead of connecting the tablet to the computer. Okay.
Okay, please.
All right. So let me repeat that because you couldn't see it, right? What new measures is how far P is from being in L2, right? And if P is not, how far F is from being in L2. If F is not in L2, I also have a problem with the first term, the d over dt of the integral of F, K convolved with F, right? So that creates additional loss of regularities. So that's new. What new measures is how far we are from having duality between F and G. So what you can see is that if both of them are if both of them are nice or are comparable, then this is all good, right? Oh, except I forgot an intermediary formula. Sorry. This is actually teach me not to do too many stupid things. There's a 1/2 here. This is 1 times 1 minus over 2 minus mu over 2. Sorry, I missed half of the formula, especially the 1/2, right? So in that case, right, if mu and nu are all equal to 0, then what I get is very simple. I get a number of derivative that is equal to 1/2 of 1 over alpha plus 1. Okay. So if alpha is equal to 0, you get half the derivative, and the larger alpha is, the less derivatives you have. So again, this is better than other averaging lemmas that you have in a similar situation, right? Pierre-Emmanuel will not give you this type of regularity. But if you try to push it the other way, right? So if F is not in L2 and P is very small, and if 1 over T plus 1 over Q is very, very large, so that means you have low integrability on F and G, then you will lose a lot by using this method, and you can actually end up being worse than classical results. Another comparison once I'm here. So I mentioned yesterday the result a little bit later than ours by Arsenault and Lerner, and in that case, so in the case mu equals 0, mu equals 0, right? They find the same regularity. what they are actually studying is they're studying a case with more general derivatives. Right. So in particular, f can have a derivative in v. And similarly, g could have derivative, also derivative in x, by the way, but including derivative in v. And those can be a positive number of derivatives. So you can have regularizing effects. So they are really interested in understanding more how hypoelliptic estimate work within that method. But they are not studying the case where P and Q are not dual. So this is really where the two approaches diverge, because you cannot do the same thing. So they are more general in terms of the derivatives that you can have, but they are less general in terms of the exponent, the integrability that you can have on f and g. When the two set of assumptions intersect, we have the same regularity, though, which is reassuring. All right, the rest of the remark are very similar to what I said before. So this is still compatible with hydrodynamic limits and so on. Now, before I give you a very, very brief idea of the proof, I want to talk about one example of application. And those are measure-valued solution to scalar conservation law. So those had been introduced by Dipernat in the 80s. And they have, well, they are becoming quite popular nowadays again, because they offer a sort of statistical description of the kind of oscillations that are possible within scalar conservation law. Okay, so what is the measure-valued solution? There are various ways of defining them, but what is maybe the simplest, given what I want to do and given what I've already talked about yesterday, is to use the kinetic formulation. So a measure-valued solution is something that you obtain as the first moment of some f, right? So this is a u of tx, and f is an f of txv as before. With f, that solves the kinetic formulation, right, with some bounded measure. Now, for the classical kinetic formulation, we had a precise form of f, right? And here we don't, so this is the big difference. So we do not impose right, so if u was positive, for example, then this was the formula, right? Instead, f can be anything between 0 and 1. All right, so this is something that you can get relatively easily if you get crazily oscillating solutions, right? Again, remember that in the classical kinetic formulation, f is the antiderivative of the Young measure. So the fact that f has this very precise form as an indicatrix function, right, is directly connected to the fact that the Young measure has one Dirac mass where it should. So if you put more than one Dirac mass, right, if you spread the Young measure, then this is what you would get. All right, so there's a lot of recent results there, and I'm not going to go into the literature, otherwise, again, I won't have time to talk about the rest. In the present context, right, what do I want to mention? Well, I still have the kinetic formulation, and u is a moment, right? So I have regularity. So if A is not degenerate in some sense, okay, and I'm not going to write down too much what it is, this is actually the condition that I had written yesterday. Then this is what you would get. So what you would get is you gain 1/5 of derivative in some Bezoff space, right? So essentially almost in L5 third. And I forgot an assumption if U is bounded, right? And F has compact support. Otherwise, you lose even more. All right, so this is the previous averaging lemma result. The new result implies that in that case, U is actually in L2 in time, HS in X, for any S strictly less than 1/4. So you see the gain, right? We had 1/5 of the derivative, now we have 1/4, and you were in L5 third, and now you're in L2. So of course, this is a very trivial application. I will start discussing a much more interesting one in the last part of my presentation today, to non-homogeneous settings. This is direct application of the theorem that I showed you before. Right? There's no additional proof. There's nothing else to add. But this shows the usefulness of having this the extra integrability in F being able to compensate the loss of regularity in the right-hand side, which is not possible in classical averaging lemma. Right. Okay. Well, sketch is even maybe too much for what I'm actually going to say. So what is the main idea in the proof, in what we are doing, to be able to handle something like that? And the point is, we are going to renormalize the equation, so we are going to modify it, right? But this has to be done in the right manner. And this is a modifier in V, but at a scale that depends on the frequency in X. So one way to think about it is now to do first a partial Fourier transform in X, which I'm going to denote by a tilde instead of a hat for the full Fourier transform in X and V. And it's not the Fourier transform of the first version of averaging lemma, the classical one that I had showed you yesterday, which does a Fourier transform in T and X. So okay, so you have a very simple equation here. And now I can properly define my convolution. So what I'm doing here is I'm convolving in V at some scales 2 to the k, 2 to the minus k. Right, so I'm taking some smooth function as usual, right? And this 2 to the k is of the same order as the frequency in x. All right. And now I'm looking at capital F, which is the convolution of f tilde in V with that phi. Let's call it phi 0. And we try to apply the method to capital F. And what the equation on capital F looks like is almost the same, but because I'm doing a convolution, right, and I have this V grad x, which has become a V dot psi, right, I will pay with a commutator term, like in Pierre-Emmanuel's in the theory of renormalized solution. And now when I'm applying the method, I'm good. I'm good because I have extra integrability in capital F, right? So whenever I have some dual expression, something like that, or when I have derivative in velocity, I can handle that. I will use the regularity given by phi, and this will pay with some power of psi, right? So every time I don't have duality, every time I have some derivative in V, then I'm paying with some power of psi. On the other hand, the commutator term, right, is behaving like a power of psi, an inverse power of psi itself. So then it's an optimization game in between all of this. Right. And the optimization that I control is the theta, right, which tells me what is the size of the regularization in V with respect to the size of the frequency in X. So once you have this idea, the rest is technical, it's painful, and it's more complicated than what I'm saying here, of course. But there's nothing really very, very smart in the rest. You have to do things very carefully. And you have to understand how to do Calderon-Zygmunt estimate on phi like this, right? Which is another question you might have. Meaning, when I'm going to apply the duality, how will it work with such kernels? So you have to, do a certain number of technical steps here. All right, so this is the main the main sketch of the proof in the non-dual case with derivatives. Now, in the last in the last 10 minutes, I want to talk about start talking about the inhomogeneous case. And this is really about an equation like that. And the big thing here is, of course, that now I have this x dependence in the velocity. Now, for simplicity, I will not consider here any sort of extra derivative, right? We are actually working on the second paper around that, and then we will put the extra derivative and everything. And you can combine the idea that I'm going to talk about tomorrow with the renormalization method that I've just talked about, and it works, but I really don't want to go into that during this mini class. And for the same reason, I'm going to assume duality always, right? So F is in LT, L infinity in time of LP in X, right? G is in L1 of time LQ of X. With P larger than 2 and 1 over P plus 1 over Q less or equal than 1. And finally, I mean, this wouldn't necessarily be a very big thing, but it is useful. I'm going to assume that the divergence of A in X is 0. If it's bounded, so if A is reasonably smooth in X, which it is, in the result I'm going to show tomorrow, we could do away with that, but again, this is to keep things as simple as possible. So why would you consider things like that? Well, there are plenty of cases in conservation law where you are not in a setting which is homogeneous in space. So for scalar conservation law, one may want to have spatial inhomogeneities. That means that initially, the flux would depend on X. And well, if X is the case, then of course, the small a in the kinetic formulation, right, which comes from this big A, is going to depend on x as well. Because it's the derivative of the big guy. Now, the question obviously is, could first be, well, how far can we push something like this? And there's a whole theory in scalar conservation law of that. There are now older paper by Odus and Pertam, for instance, trying to get A to be as singular in X as possible. But that's really not what I'm going to talk about tomorrow. Instead, the question I have is what remains of the gain of regularity provided by averaging lemma? And so far, the answer is nothing. In the sense that I do not know of a single result which can provide you a quantitative gain of regularity on the averages for a kinetic equation that has an explicit x dependence in the velocity field point. And one big advantage of our new method is that, as I will try to explain, it can actually deal with situations like this. So I think this is all I wanted to say for today, and it's good because it's precisely 9:55. Thank you very much.
Okay, thank you very much, Pierre-Emmanuel. There are questions, comments?
Let me bring back the webcam.
So in the first case, the coefficient A was depending only on V.
Yeah.
And actually, probably you said the derivative with respect to x commutes with the equation, something like that. So this was very important for...
This is absolutely critical. The whole point, right, is to use the commutator with the V grad x.
Yeah.
So the taking the derivative in x, right, of the kernel k was what was creating the gain of regularity.
And also for taking the Fourier transform with respect to x.
Yeah, that would be a mess, right? And that is going to be a bit of a mess.
Okay, so in the second case, so when A depends both on x and b, so
But it's explicit, right? You can calculate it, which is what I'm going to do.
Mhm.
So I'm going to pay with a derivative on A, right? I'm going to assume that A is smooth, and I will try to understand how this is working.
Mhm.